I want to again thank all of you. I have been chided several times this evening with what were you thinking keeping us this long all day? And I take complete responsibility for and take complete blame for having such a long day for all of you, but I greatly appreciate the energy and the enthusiasm that all of you have displayed throughout the day, right up to now, et cetera. I have a couple of procedural issues to mention. So we're going to go into dessert and conversations that go well with dessert. There is also, at that far end of the table, at the far end of the room there, a table with the books and stuff. We brought it down from upstairs. So after the session is over, if you want to mingle and move around briefly there before you take your shuttles back to the hotel, you're certainly welcome to do that. That shelf will again go back up tomorrow as well, so you won't miss too much. Okay, so my next order of business here is to welcome to the lectern here Dean O'Keefe. Barbara O'Keefe is the Dean of the School of Communication, and along with the Dean of Engineering, Julio Otino, who you heard from this morning, and Dean Sally Blount, the Dean of Kellogg, have been very generous in providing support to host this event here, and I want to welcome Barb.
Thank you, Nash. I understand I'm not the only dean in the room. There's another new dean somewhere in the room. Where is she? No? Ah, hi, Wendy. Welcome to the club.
She's a dean.
I'm actually going to have a little advice in the middle of this talk. So, I've been very fortunate to be dean of the School of Communication at Northwestern, which is the oldest and arguably the year in and year out greatest communications school in the world. So it's really fun to be in this role. But I came to the role very fresh. I mean, I wasn't somebody who had been in a lot of regular academic leadership positions like department chair or associate dean or whatever. I came up through leadership positions on the research side, lab director, center director, and so on. And so when I became dean of the school, I knew the job was going to be different than my past experience. And I especially worried about events like this. I wondered, oh my God, I'm going to have to go and open these conferences and things like that. And especially in a big school like this one, where you've got everything from people who study the neurological basis of speech and hearing, to people who study networks, to people who do radio, TV, film, to people who do theater, including music, theater, and dance. You naturally wonder what in the world you will say when you get up at events like this. Well, it turned out that it's a lot easier than I thought. Number one, people have very low expectations of deans. But then I also found that empirically speaking, there are three fairly simple things that a dean is usually called on to say. It turns out that all three are appropriate tonight. The first thing we do is welcome people. And I do indeed want to welcome all of you to Northwestern and to this third international workshop on network theory. We're especially delighted that the directors and trustees of the Web Science Trust have been able to join us for this meeting so that we can truly meet our goal of exploring the connections between web science and the science of networks. So welcome to all of you and especially to them. The second thing deans usually need to do is thank people. And I do indeed want to thank everyone who's contributed to making this meeting possible. First and foremost, I want to thank Noshir Contractor and the members of his Sonic Lab for doing such a spectacular job. And second, I want to thank Nasha's partners and collaborators from the University of Southern California, Janet Folk, Peter Manji, and Manuel Castel. I'm especially grateful for their long-standing and productive collaboration with faculty here at Northwestern. And I'm sure you all appreciate the way in which that particular group has advanced this area in many ways, from the development of new research methods and shared graduate training models to new research and theory. And then third, I want to thank our partners from the Northwestern Institute for Complex Organizations, and especially Brian Utsi and Kevin Lynch. I, again, am especially sensitive, having worked here to build a great faculty in this area, to everything that Nico has done to change the face of Northwestern and make it an especially receptive environment for research on networks and web science, team science, and all the other topics in which we currently have an interest. Now, I'm sad to say that the third thing that deans usually need to do is say, I'm sorry. And often it's saying you're sorry even when you didn't have anything to do with whatever it was that went wrong. So let me say, I'm sorry for the horrible weather we gave you, which is exactly the kind of thing we usually say I'm sorry for. It really was a lot nicer until today, and now we've got this really unbelievably nasty weather for you. But I actually heartfelt want to say I'm sorry because I haven't been able to be more of a participant in this meeting. I started to fill out my little network survey and realized that, in fact, I know an awful lot of you for various reasons, not just because some of you are from Northwestern, but from far-flung places. I know many of you, your colleagues and friends and people who've helped me in various ways in my work. And I would very much have liked to be more of a participant in this workshop. The topic of this meeting is one that I see as absolutely critical for our progress in the communication sciences. There are few areas that I am putting more emphasis on in the School of Communication or more energy into in terms of developing the environment at Northwestern. So, unfortunately, I am a dean, not just a researcher like most of you. And in a big, busy school like this one, there are always many, many demands on a dean's time. For example, we have a big deal thing going on in the theater department this weekend, and I had to divide my time between you and them. Hence my regret. I wish I could have been here all day with you for my own sake, yet I could not. In closing, let me emphasize again how utterly delighted I am to see this meeting happening at Northwestern. When I came here a decade ago, I came from Michigan. I was in the School of Information there. I was running a research center. And I was determined to see this university develop a vibrant community of scholars studying social networks, network digital technologies, and their co-evolution. I've been extraordinarily gratified to see Northwestern develop a strong commitment to interdisciplinary research on this topic and to find great partners all around Northwestern to help me achieve my goals, and particularly the McCormick School of Engineering. And you talked to Dean Otino this morning, who's been as committed as I have to making things work in this area. With this kind of institutional commitment, we've been able to attract a group of very dynamic and creative young scholars, and they've begun to bring people like you, their partners and collaborators, to interact with us here in Evanston. It has made this place the university I hoped it would become when I came here. And so it's not mere politeness, but the down-to-earth, literal truth that I could not be more pleased to address all of you here tonight and welcome you to Northwestern.
Okay, you all very well behaved through that. I think the service will continue. I know some of you are waiting for refills on glasses of wine and dessert, and I think the service is going to continue now on that. And now we're ready to introduce our keynote speaker, dinner speaker tonight, who has been asking me to pick up the pace here and do this sooner rather than later because he was afraid that he's been trying to pace his beverages all evening and wanted to make sure that we didn't delay it too much. I tried to delay it as much as I can because I've had the opportunity of welcoming Duncan to give a dinner speech before, and I know this was at the Social Networks Conference back in 2000, and so I have some experience of what you really are in for a treat. He assures me that today is less of a dinner talk and more of a technical talk, but knowing Duncan, I know that's not going to be an issue. I'm not going to introduce Duncan because if any one of you doesn't know Duncan, then you ought not to be in this meeting. What I will do is say that I will pull in the plug, and this is actually part of what motivated us to do this, is Duncan has a new book coming out. It's called Everything is Obvious, asterisk, Once You Know the Answer. You might recall from this evening, at the last talk, when Sinan gave his results, Duncan said something about this issue. And I knew exactly why he was asking that question. It's been on his mind. Everything is obvious, including Sinan's results. So Duncan's book was supposed to be out by now, in which case we would have had copies of it. We actually will have some copies delivered on Monday, but the book doesn't officially come out till next month. Is that right, Duncan? And I'm very pleased that this event today will be his first book tour talk, if you want to call it that. So Duncan, take it away.
Thanks, Nosh. I think traditionally dinner speakers are supposed to, shower you with witticisms and anecdotes as you enjoy your dessert. Unfortunately, Nosh didn't really tell me how brutal today was going to be, and so I just prepared my usual sort of talk, which you're not even going to be able to see. Can we, what's going on here? How is the Mac not doing its magic? Okay, that is, we're almost there. Brilliant. Okay, so I'm actually going to talk about some research that is very much sort of hot off the press. It's work that I've been doing with my one of my team at Yahoo, Winter Mason, who is a psychologist. And we're interested in, as the title says, collaborative learning in networks, and then I'll say a little bit about web-based experiments. So here's the outline. I want to start out by just sort of giving you a little bit of a background about why we're interested in this problem, and then sort of zoom down from the general kind of question and to a particular set of experiments that we've been working on recently at Yahoo, and then again sort of zoom out a little bit, except in a kind of an orthogonal direction from the substantive question to more of sort of a methodological question. Ask, sort of conclude with some very speculative remarks about where this might be going in terms of the sorts of things we can do on the web now and the implications for experimental social science. So, this is a little bit preaching to the choir here, but I think it's a reasonable statement to say that many problems in fields that we're interested in, both in science and business and also engineering, are complex. And this word, I used to be a postdoc at the Santa Fe Institute, and so if you've spent any time at SFI, you know that the word complexity it's like a Rorschach test for the listener. It can be used to mean almost anything. What I mean by it here is that the sorts of problems that we tend to solve in large organizations in the real world are characterized by having two sort of very salient attributes. One is that they have a multiplicity of potential solutions. So, in any competitive landscape, there are typically many kinds of designs or strategies or procedures that could have worked, that could have succeeded, or possibly have succeeded. And it's sort of a priori unclear how to rank these or how to decide, map a set of attributes to a performance metric. The second thing that makes complex problems complex is that you have these very strong interdependencies between the different dimensions of an attribute. So if you think about building a jet engine or even a car, you don't necessarily want each individual component to be as sort of, it's actually kind of meaningless to even sort of specify how you would sort of optimize each individual component in isolation of the others. Clearly, how you design the gearbox has implications for what you do with the drivetrain and the wheels and the chassis of a motor vehicle. And almost all like real-world design problems have this kind of feature where the effect of changing one parameter can have very different, can be very, very different depending on the settings of the other parameters. Now, actually sort of formalizing these concepts, you sort of state them and everybody nods their heads and says this sounds right. Actually formalizing this is very, very hard to do. And there have been a number of attempts over the years, and possibly the most popular ones have stemmed from Stuart Kaufman's model, or the NK model. But one sort of useful, at least metaphor, which in this talk I will turn into a real thing, is what people refer to as a fitness landscape. This actually came out of population genetics. The idea that you map this sort of high-dimensional space to some kind of fitness, and that you can sort of move around this landscape as a person would move around on a real landscape, and that you have, in a complex problem, is characterized by a rugged fitness landscape where you have many peaks of different heights, but typically getting from one peak to another peak involves going down into a valley. And so what that leads to is the next very sort of general level observation about complex problems, which is that when we try to solve complex problems, we, in trying to navigate this rugged fitness landscape, have to strike some sort of trade-off between two general strategies. One is exploitation and the other is exploration. So exploitation is where you take the thing that you know how to do already, or you take the best known solution and you copy it and you beat the hell out of it. And then exploration is where you sort of think that there must be some better way to do things, and so you invest in some sort of costly search exercise to find a better solution. And of course, too much of either of these things is bad, right? Like most things in the social world, too much of anything is a bad thing. So too much exploitation leads to sort of suboptimal long-run performance, but too much exploration is also problematic because you never actually get to benefit from what you've already learned. Now, so this is, you know, I work with computer scientists today, and they sort of look at me like, you know, and of course we know that exploitation is important. There's sort of everything in machine learning and most of modern computer science has something to do with exploration, exploitation. So there's lots of different problems and algorithms that are associated with complex optimization. And it's actually interesting to talk to computer scientists about this problem as coming from a social science background, because they sort of imagine that an organization should really be like some sort of you know, Markov chain process, and it's sort of trivial, right? But actually, I'm less concerned with what the optimal way to solve problems is, you know, in theory, and more concerned about how people actually solve them, right? So what do real fitness landscapes look like, and what do real human problem solvers, what sorts of strategies do real human problem solvers adopt when they're faced with these sorts of problems? And I don't really care at all about whether they are sort of executing things as well as a Metropolis algorithm. So there's actually lots of work, of course, in social science as well, from Radner's team theory to Simon's bounded rationality, March's early work on organizational learning, lots of models, evolutionary models of organizations. So again, this is a very, very general problem. It sort of comes up everywhere. And what makes it, the other kind of wrinkle that I want to point out here is that in many of these real world contexts, and probably all of them, people are not solving these complex problems alone, right? That they are trying to sort of strike these trade-offs between exploring for new solutions and exploiting known solutions in the context of other people doing the same thing, where there's some ability to learn from the experience of others. So this can be very helpful because not everybody has to solve every problem from scratch. I mean, all of human civilization, in a sense, is based on the fact that one person can solve the problem, and then everybody can learn from them. And so there's tremendous benefits from collaboration in complex problem solving. But on the other hand, too much of this learning can lead to herd-like behavior where we all sort of glom onto some kind of suboptimal solution when possibly a little bit more exploration would have generated a better solution still. And so you might suspect, and there's lots of theories and models that support this suspicion, that somehow the way information flows throughout an organization might have something to say about its problem-solving capabilities. And so this has lots of implications, not just for organizations, but also for individuals. And there are sort of interesting kind of questions about how an individual's position in a network not only can affect their own performance, but can affect the organization's performance. So the individuals who are in central or brokerage positions can gain from exposure to novel information. You might wonder about how that affects the performance of the whole organization when everybody is trying to do that. Let's see. Right. So there's sort of interesting questions about the sort of tension between individuals trying to maximize their own network position or play a particular strategy given their network position, and how that affects the collective performance. So sort of lumping all of these questions together, we're interested in a few substantive questions, which is, first of all, how do individuals actually behave when they're collaborating on these complex problems? How does the structure of the communication network between them contribute or affect their collective performance? And what is this relationship between individual performance and collective performance? So the way we're going to go about this, and this is a question I've been interested in for many years, and one of the, sort of previously we've tried to sort of think about this problem from a more of a sort of agent-based modeling or simulation perspective. And one of the problems you always run into with these sorts of exercises is that you have to model how people behave. And one of the nice things about doing an experimental approach to this is that you actually just get real people and they just do whatever they do. But of course, now you have to run experiments where you have very large numbers of people interacting over networks, and this produces its own set of problems about the practicality of doing that. And so in recent years, and I'll maybe talk a little bit more about this at the end, we've made a lot of progress in using the web as a kind of virtual laboratory, and that has certain advantages and some disadvantages for this kind of experimental science. Okay, so here's the experiment. It's called Wildcat Wells. The name doesn't really matter, but it is sort of evocative of the kind of game that people are going to be playing. So you arrive at our website. We recruit people. By the way, many of you are probably not familiar with Amazon's Mechanical Turk. This is a site that was created by Amazon about 5 or 6 years ago to do what's called crowdsourcing, where you pay large numbers of individuals small amounts of money to really do sort of micro tasks. And it's become very popular, particularly for online work that is easy for people to do and difficult for machines to do, such as labeling images or characterizing the sentiment of websites and so on. Is what Jeff Bezos calls artificial intelligence. The original Mechanical Turk, of course, was a chess-playing automaton, which was famous for having beaten Napoleon. But of course, it was actually a hoax. There was a person inside the automaton playing all the moves, hence the artificial intelligence. So for sort of a nice backstory to Mechanical Turk, the way we think of Mechanical Turk is the 21st century equivalent of putting flyers up around campus and getting students to come to the psych lab to participate in an experiment. It's effectively just, for us, a recruiting and payment mechanism. But it has some very nice features in that regard. Nevertheless, you come through Amazon and you end up basically looking at this website. And once you sign in and agree to the terms of service, you are shown a screen that looks like this. So this is actually an aerial shot of somewhere in California. And the idea is that you're supposed to pick a location and drill for oil, right? So you're looking, you're trying to, there's some sort of hidden payoff function under the landscape here that you can imagine as oil fields. And you're punching a hole in the ground and you're getting a score. right? So the top left-hand corner is, after round 1, the score that you've received. You also, this is all explained to you in the instructions, you also are assigned 3 collaborators, your neighbors, who are players A, B, and C, and you, in addition to seeing where you drilled and the score that you got, you also see where they drilled and the scores that they got, right? So you're getting some information about things that are happening elsewhere that your collaborators, information that your collaborators are generating, and you can choose to pay attention to that or ignore it as you please. So as the game goes on, you now pick a new place to drill, and you can either type in the coordinates or just click on the screen, and then the game goes on, and you can see after a few rounds, one of your neighbors has actually found this spot up in the top right corner, which looks like rather a high score, and so you may want to pay attention to that, and well, sure enough, people can find the peak or the optimum of this landscape. Now, what you don't know is that underneath this sort of superficial landscape is this fitness landscape. And if I'm confusing by using the word landscape in 2 senses, I should probably use surface to describe or topology or something, topography to describe the first landscape. The fitness landscape is something that you're not actually, is not actually revealed to you. And what it composes, it's composed of 2 pieces really. There's this sort of background noise function, which we generate with what's called Perlin noise. I don't know if you're familiar with this, but this is when you see computer-generated graphics in movies, there's sort of surfaces that look real or look like mountain ranges or rough, sort of realistic-looking surfaces, trees, etc. It's all generated with this interesting algorithm that an NYU professor came up with about 20 years ago. So it's called Perlin noise. It's just a way of generating sort of smooth, random-looking surfaces. And as you can see, there are many peaks in this 2-dimensional surface. And then we superpose on that a single peak, which is in some sense like the best solution. And all of this is then normalized between 0 and 100. Okay, so this is the landscape that you're actually navigating, but you're just doing it sort of blindly. So the other thing that you can't see as a participant is that you and your 3 collaborators are part of this larger network, right? So in this case, all the network we consider have 16 individuals, and they're connected to each other through a network where everybody has exactly the same number of neighbors. So everybody has 3 neighbors, and so all people have exactly the same amount of information and exactly the same view of the world, right? They just see themselves and their 3 collaborators. And how we create these networks is we start out with fixed degree random regular graphs, and then systematically rewire them to optimize some sort of function of a particular network metric. So we're interested in betweenness centrality, closeness centrality, clustering coefficient, network constraint. These are all, I'll define those in a second, they're all parameters that people have studied over the years in conjunction with information diffusion and individual performance in networks. And we're interested in the maximum, the average, and the variance of these different metrics. And so we have this rewiring process that maximizes some function of these metrics, and then we stop when we've maximized that, and we do this many times. Many of these networks turn out to be, these maximal or maximizing networks turn out to be redundant. So I'll show you in a second that we can actually reduce our selection of networks to just 8. But just to review briefly, for those of you who are not familiar with these terms, clustering coefficient is just the average probability that the 2 of your neighbors are connected to themselves. This is also called local density. Betweenness centrality is the number of, if you count the number of shortest paths between all pairs of nodes in a network, your betweenness centrality is the number of such paths that you lie on. Closeness centrality is your average shortest path to all other nodes. And network constraint is something that Ron Burt can explain to you afterwards, because I think he's responsible for this particular formula. But to some extent, to sort of intuitively, it's just the redundancy that your neighborhood experiences. So it's actually pretty closely related to clustering, but not exactly the same. Okay, so what do we get after that somewhat complicated exercise? Well, we get 8 different networks, and roughly speaking, you can see that they break down into 2 subfamilies. The bottom row all look somewhat like random graphs, right? So very little clustering. The one on the bottom right-hand side is a little bit different. It has a little bit of clustering, but is highly decentralized, as a random graph would be. The ones on the top all have some sort of center. Well, the one on the top right-hand side has a very obvious center. It's really a hub and spoke network. You have 2 that are sort of like lines and one that's like a cycle. Okay, so there's a fairly sort of, in some sense, if you take the family of, or the universe of all networks of 16 nodes with 3 neighbors for each node, this is about as wide a spectrum of possibilities as you can get. Now, obviously, if you have bigger networks, then you have more possibilities, but we're trying here to sort of span the greatest range of topologies that we can under those constraints. So now we run the experiments. One problem that we've had to solve over the last couple of years is that, unlike early experiments conducted on the web, which were sort of designed so that one person could participate at a time, so people would sort of arrive effectively in a queue and they would participate and then they would leave and somebody else would come in. These experiments require 16 people to be present simultaneously and to stick around for the whole game. And this is something that you can sort of solve by brute force in a physical lab by having a lab proctor stand there and sort of with their arms crossed looking very stern, and people tend not to just sort of walk out of the lab even though they could halfway through the experiment. Online, where you have people logging in at work or from home or wherever, different time zones potentially, it's much more difficult to get them to arrive at the same time and then stick around. So the way we solve this problem is to run a series of smaller experiments and then recruit people to a standing panel, which we then, we have their contact details, and then once we get a big enough panel, we then email them or message them through the mechanical Turk system the night before and say, tomorrow we're going to be playing games at 11 a.m., 1 p.m., 3 p.m., and 5 p.m. We will ping you again 5 minutes beforehand. Please show up. So people show up. We put them into a virtual waiting room where they sit there and there's a counter ticking down. And as soon as we have 16 people, we sort of pinch that group off and a game starts. And then we try to fill up the waiting room again. And this system actually works pretty well. Nevertheless, we do have a certain number of games in which somebody goes off to the bathroom while they're in the waiting room, and then by the time they get back, the game's already half over. And so we have these sorts of random events, and we've had to exclude a bunch of games because of them. The way we organize these games is into sessions. So each experimental session has 8 games. Each game is one of these 8 network topologies, which we present in random order. So everybody plays one topology. The same group of people play each topology per session. Each game runs for 15 rounds. So people are now searching in a 100 by 100 grid. And we did some sort of pre-testing to try to select the relative diameter of that main peak that I showed you, so that it wasn't so difficult to find that nobody ever found it, and it wasn't so easy to find that they always found it. Right? We wanted to have as much potential for differential performance there as we could. Okay, so we have a total of 171 games over 25 sessions. So just to summarize the results before I get there, remember, we're interested in individual performance, we're interested in group performance, and we're interested in the relationship between the two. So we do find that network structure affects individual search strategy. This is actually more surprising than it sounds, and I'll try to make that point. We also find that individual search strategy affects group success. That seems relatively straightforward. Network structure also affects group success directly through an information diffusion process, a little bit like the Centola paper that Michael mentioned. Well, actually, not like the Centola paper. It's a different kind of diffusion, but same general point that Michael mentioned earlier today. And finally, that there's this sort of interesting tension between individual and group performance. So here's the first result. The bars are ordered from the top. You have the networks that have very low clustering. So red means little clustering, and the numbers are actually the clustering coefficients of those networks. And then the purple and blue networks are the ones that have the higher clustering. And you can see that there is, so the x-axis is the proportion of rounds in which exploration takes place before the peak is found. So we make a distinction between instances where the peak is found and where it is not found, because the desirable kind of behavior changes once the peak is found. Before the peak is found, obviously you're trying to find the peak. And so, so there's an interesting, the sort of, the main question is whether people are exploring or else they're simply just copying the best. So by exploitation here, we mean copying the best available solution or one of the solutions of your neighbors. And so you can see quite clearly that in networks with no clustering, there's a lot more exploring going on in networks with clustering. Now, why is this surprising? It's surprising because you can't actually tell how much clustering there is in your network. All these players, regardless of the network that they're in, have exactly the same view of the world. They just see three neighbors. They don't know how they're connected to each other. They're given no information about anything to do with the network. Nevertheless, this invisible network topology is actually affecting the way that they play. So why is this? Well, there's a sort of two-step reasoning process here. The more clustering you have in the network, the higher the probability is of two of your neighbors guessing the same location, right? So if your neighbors cannot see each other's locations, then the chances of them randomly choosing the same, of 1 of 10,000 grid squares is effectively 1 in 10,000, so almost zero. But if they can see each other, then there's some possibility that one of them might copy the other one, right? And sure enough, the more sort of interconnections there are between your neighbors, the more likely that is to happen, right? Now the second step is that the more of your friends you see copying each other, the more likely you are to copy them, right? So, and that's not so obvious that that's what you would want to do, but in fact, that is what people do, and that's what the bottom figure shows. In all instances, copying increases over time, which is something you might expect. Early on in the game, people are trying to explore. Later on in the game, they're trying to exploit. But they do more exploitation over the whole course of the game when their neighbors are copying each other. So the combination of these two factors means that highly clustered networks result in more copying than networks with no clustering, even though the network itself is not visible to the players. So this is copying, as you might suspect, is actually bad for group performance before the peak is found, because if everybody's just glomming onto the best solution that they can see, they're very unlikely to find the peak. And sure enough, you can see that as the proportion of players who are copying increases, the likelihood of finding the peak in the next round goes down dramatically. And so you might think, okay, networks that are highly clustered are going to do worse than networks that have no clustering, and that's sort of true. If you look at, this is the bars ordered in the same way as before, and you can see that indeed the ones at the top sort of look like they're like the proportion of games in which the peak is found is higher for those networks, but the error bars are big enough that we can't actually get any significance here. So maybe that just means we have to do 1,000 trials instead of a couple of hundred. I think the sort of combination of indirect effects got too much for our numbers. But it is at least suggestive that reasoning that I described to you is on track. Okay. I think that's just another gratuitous picture of networks. So the next result is sort of about what happens after the peak is found, right? So this is, up till now, it's all been about exploring and trying to find this peak. Now, once somebody finds the peak, you might expect that that information is going to start diffusing through the network. And indeed, here you see a very clear partition between, I guess maybe that's why we have this picture here again, between essentially the top row and the bottom row. So all the networks on the bottom row are in black to the left, and all the networks on the top row are in light grey to the right. And so, and the x-axis here is the number of rounds after somebody finds the peak. So this is how rapidly is that information diffusing through the network, and you can see that it's basically spreading. It's spreading in all cases, but it's spreading faster in these decentralized networks. And we just have a little movie here. Well, it's not really a movie, but a series of slides where you have a decentralized network on the right and a sort of chain, one-dimensional chain structure on the left. And you can see that in both cases, they're getting closer. So here, a lighter color is better. So someone on the right there is doing fairly well. Do I have a pointer here? Yeah, so this guy is getting close, but then someone discovers the peak over here. You can see that this information is already spreading to this person's neighbors. So the network on the left actually has a head start of the network on the right. Now this person has found the maximum value, right? So this is now, they have 100 points, and you can see the difference here that this person has now got to the maximum. But on this side, it's going to have to diffuse all the way around, whereas on the right-hand side, you can see that it's reached everywhere in just 3 steps. So now it's still diffusing, still diffusing, still diffusing, still diffusing, right? So you can see that essentially the diameter of the network really dominates the speed with which desirable information spreads. Okay. So network structure affects individual performance, network structure affects group performance, and now there's this sort of tension between the two. So we saw before that the more players are copying, the worse or the less likely they are to find the peak on the next round. What this bottom picture shows is that finding the peak is the single most important thing in terms of overall performance. So here is all the runs in which the peak was not found, and here are the runs in which the peak was found. So this is a sort of very bimodal distribution of payoffs. You either find the peak, in which case everybody gloms onto that and everybody does very well, or you spend your time wandering around in the wilderness looking for this peak. So it's true, and you would expect it to be true, that because too much copying makes this outcome less likely, that it's bad for collective performance to do too much copying. Interestingly, however, it's better for individuals to copy, right? So this is this plot here is the this is now each dot here is a particular participant, and the size of the circle is related to the number of times that they've played the game. So you can see that this result is not affected by experience. Right? The same general trend applies to people who have played many times or just a few times. And the more they copy, the better they do. Right? So this is interesting because it suggests that there is something like a social dilemma going on here. Well, not even something like, it is a social dilemma. That individually, players are better off just taking the best available information, basically letting your friends do all the exploration and then free riding on them and taking the best result that they can get. But collectively, the group is better off if individuals agree to do some exploration. And what I thought was interesting was that when I was writing this up, I went back and read Jim March's paper from 1991. I see Woody nodding over there. And he has a completely different model of organizational problem solving. And it's a simulation model, and every sort of assumption is different. And he comes up with exactly the same finding. So there was this sort of very nice kind of symmetry. 20 years later, we see the payoff function is different, and there's no networks in March's formulation. He's got sort of heuristic rules. We have real people. So everything is different. And yet this result comes out very strongly in both cases. So I thought that was particularly striking to find this sort of social dilemma coming up again. The other kind of tension we see between individual and group performance has to do with the which network you want to be in versus where you want to be in a network. Right? So what this shows is that, so this is now the number of rounds required for an individual to get the maximum score after somebody finds the maximum score. So lower numbers are better here, right? And on this, so for each network, we have the best person, the median, and the worst person. And so again, you can see that these are all the decentralized networks up the top, and they're all, the worst person is basically level with the median person in the centralized networks, and the best scoring person in the centralized networks is about level with the median person in the decentralized network. So overall, you prefer to be in, if you care about absolute performance, you would always prefer to be in a decentralized network. Everyone should want to be in a decentralized network. If you care about relative performance, however, you can see that the best people in these centralized networks do a lot better than the worst people, right? So the differences in performance within a network are bigger in the centralized networks than in the decentralized networks, where essentially everyone is the same in the decentralized network. So, and so you can sort of see that here, that this guy who is the hub of the hub and spoke network is only doing about as well as just about everybody over here. So almost everyone in this network is doing as well as the best person in this network, but they actually all look the same to each other, right? So this guy is actually probably happier because he's doing so much better than everybody else. So we didn't endogenize the network in this particular experiment, but you could sort of imagine an extension of this where people get to decide whether the network should be allowed to change. If this person happens to be in charge of the organization, he may be very happy with the way things are. But that's not necessarily the social welfare maximizing solution. Okay. So just to go over the results again, network structure affects individual search strategy. And again, just in case you thought that was an obvious point, we did another whole set of experiments recently where we played public goods games on different kinds of networks, and we found no effect of the network structure on individual strategy at all. And when this paper was reviewed, the reviewers said, yeah, that's obvious. Of course, they couldn't see the network. How can anyone condition their strategy on the network if it's invisible to them? And so here's the answer. Sometimes they do change their strategy even though they can't see the network, because the network the network structure is manifesting itself through the information, indirectly through the information flows between your neighbors. Once you get that point, then it seems clear that individual search strategy should affect group success, and we think that it does. It's very clear that there is this direct effect that is a function of diffusion. And then finally, there's, I think, sort of the most interesting results of this to do with how individual and collective performance can be in tension with each other. So obviously, there are many limitations to this particular research with respect to real-world problem solving. I don't think I even really know what real-world problem solving is. I've thought about it for many years, and every attempt to sort of formalize it has turned into a complete quagmire. You know, it's obviously true that real-world problems are much more high-dimensional than the two-dimensional problems that we've considered here. It's really sort of unclear what the interpretation of this, you know, this sort of made-up, you know, fitness landscape is that we proposed. And of course, these networks don't really look like real-world organizational networks. There's no hierarchy, there's no power, you know, there's no specialization or division of labor. You know, so there's lots of artificial elements to the particular networks that we've chosen. And finally, it's not, you know, the incentives are, you know, people don't have any incentives in this game to deceive each other, right, or to you know, to not disclose information, to play strategically. So you know, I want to be cautious about inferring too much about real-world results. It's really just sort of, this is the first step in what we imagine to be a long process of looking at more and more realistic problems. But I do find it sort of encouraging that some of the results are familiar from earlier studies. And certainly the experimental platform should generalize to more realistic scenarios. And so I just want to sort of finish on that note about, you know, where does this fit into this longer story or broader story of, or really just orthogonal story of web-based experimentation. So, you know, the question is motivated, the experiment's motivated by a sort of substantive question, but it also contributes to this sort of small literature on using the web as a lab. And the sort of the main contribution here, and also this work with Sid Suri on public goods experiments has really sort of been able to crack this problem that we bumped against for a few years of how to run synchronized experiments. And so now, you know, our imaginations are running wild, and we're thinking, you know, what if we had, you know, 100,000 people in our panel, or, you know, or 1 million people in our panel? I mean, certainly at Yahoo, those numbers are not even big. You know, what could we do? Well, one thing we could do is sample from that panel. So we could say, let's just have some games in which there are all women, or all men, or all teenagers, or all seniors. So we could do all sorts of sampling on particular demographic variables. But a more interesting thing that we could do is sample based on how they've played in the past, right? So we could say, you know, some of these people have played the game many times. In Sid's experiments, we have some people who have played 50 experiments over the course of a couple of months. And remarkably, they play the same way after 50 experiments that they played in the first experiment. So this is sort of just sort of a byproduct of being able to run many, many, many experiments. And we sort of saw a result that no one had observed before, and that wasn't even a result we were looking for, just because by accident we were able to get this sort of experience with, or get these players who are very experienced. So now we can say, well, let's sample people based on the generosity that they've displayed in the past, or we want to get, if we take a group of people who have been explorers in this game, we put them all together, do they do more exploration, or do they sort of revert to the mean, and do we get the same distribution as we got earlier? How do we, you know, we can start to connect individual players across different experiments. So do people who contribute more in public goods games also explore more in these exploration games? So these are the sorts of questions that have not even been available to be asked in traditional lab studies, because you simply can't get these panels to run many, many times. Another interesting thing that we sort of discovered by accident is that what we call the hypothesis testing loop speeds up dramatically, right? So we're literally running these experiments, and we think, oh, you know, an interesting baseline condition that we should have checked is, how would they behave if there was no network at all? What if we just sort of threw 16 individuals out there with no network? And so we thought, I wish we'd thought of that before we did the experiments. And then I said, well, how much work is that? Can we just change the code a little bit? So sure enough, Winter runs the experiments the next day, right? So you don't have to sort of go back to the NSF and get another, a couple of $100,000 grants and plan things out 6 months in advance. But you can actually sort of shrink that learning cycle from a year to a day. So that's interesting. And then, of course, the final thing is that the scale of these networks can be obviously is limited only by the size of the panel that you can recruit. And right now we have maybe a couple of hundred people in our panel, but there's no reason why it couldn't be a couple of million. In 1969, Morris Zeldich, the sociologist, wrote this very provocative paper that was titled, "Can You Put an Army in a Lab?" And he was inquiring about the possibility of experimental macro-sociology. And at the time, his conclusion was, no, you can't do it. And so sociology should really focus on small group research and then rely on theory to scale the conclusions up to large groups. Coincidentally, 1969 was also the year that the internet was invented, when the first packets were sent from UCLA to SRI. So obviously things have changed a lot in that last 40 years or so. We are wondering if it's time to revisit Zeldich's question. Now, I don't want to get too carried away here. There are lots of things that real armies do that would be very hard to put online. There are lots of problems that social scientists care about that are not virtual, that involve sort of real people doing physical things in the physical world. It's not sort of clear how generalizable this model is. Nevertheless, there's clearly a lot that we can do, a lot more that we can do than we have done so far. And it should be, many of these limitations, certainly not all of them, but many of them, I think, should be viewed as a challenge rather than as a reason not to proceed. So thank you very much. Here's the requisite book plug. Although it's a little redundant now that Nosh has already so generously mentioned it, I won't really try to summarize what it's about. The title sort of says it, but it's, roughly speaking, it's, why is the social world so complex and unpredictable, and why, in spite of that, do we continue to act as if it is actually not so complex and unpredictable? Why, if it's so much more difficult than rocket science, does it seem like it's not rocket science? And finally, what can we do better? Thank you.